Good morning. We've got a few more things that we need to pick up with vectors, a few definitions that we missed the other day. Now we recall all of our vectors. We've got our geometric vectors. The next thing that we have is what we call a position vector. That's the vector between 2 points. So we're going to find a vector PQ between two given points, P and Q. Just a matter of slope. So here we've got the point 3, -2. That's 1, 2, 3, 1, 2. We've got the coordinate P here. We've got the coordinate Q is 7, -4, 1, 2, 3, 4, 5, 6, 7, 1, 2, 3, 4. It's almost as if it was set up intentionally for that. Q. So the vector, the position vector, we would say PQ, is the vector starting at P, terminating at Q. Now, it's really a roadmap of how do we get from one point to the next. What I see is vertically we are going down 2, horizontally, we are traversing 4 to the right. So our position vector PQ is going to be, we have moved 4 units horizontally to the right, we've moved 2 units vertically down. Our position vector is 4, -2. Another way we could have gotten that is if we take the y2 value, we subtract, the x value, 7, subtract 3, -4, subtract -2, and we have the position vector, once again, 4, -2. In general terms, given 2 points, x1, y1, and q, x2, y2, position vector from P to Q is going to be x2 minus x1, y2 minus y1. Position vector. How do you move from one point to another? So what are you moving horizontally? What are you moving vertically? Next up, we've got the idea called a unit vector. Unit vector is any vector of magnitude 1 in the same direction as another given vector. Now, just notation-wise, the double vertical lines, that's our symbol for magnitude. So if we take a generic random vector, I'm going to do this as, let's say, 5, 12. So horizontally we're moving 5, vertically we're moving in 12. We know that the magnitude of this is 13. We know that based upon the Pythagorean theorem. We've got a square root of 5 squared plus 12 squared. It's a square root of 169. We've got 13. So the magnitude of this is 13. Now, if we are to map this out, 1, 2, 3, 4, 5, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. There's our vector V. We're going in one direction. We move 5 units horizontally to the right, 12 units vertically up. Well, the idea behind the position vector is we want something, the unit vector is that we want a vector of length 1, magnitude of only 1, going in that same direction. So what I think about is magnitude 1, that is 1/13 the size. So what we do is our unit vector notation, we use V with a hat, we say V hat, is a matter of, it is 1/13 the size of our vector. Or we've got 1/13 multiplied by 5, 12. Our unit vector is going to be 5/13, 12/13. So what we did there, we found the magnitude. The unit vector is that proportion. Now, in this case, it is less than it. It might be greater than that. Why this works, let's just check that the magnitude of this is in fact 1. The magnitude is 1 for our unit vector. We would have the square root of 5/13 squared plus 12/13 squared. That's 25/169 plus 144/169. We've got the square root of 169/169. We have 1. Generalizing for any vector, for any magnitude, what we did there is it's we want a magnitude of 1. We know the magnitude is 13. So a general formula for the unit vector is a vector of magnitude 1 in the same direction. That has the same direction. Think about the slope. We take the vector and we divide by the magnitude. That's it. So, seeing what we did, we took our vector, we divided by the magnitude. There you go. Unit vector. Now with that, another notation for our algebraic vectors, rather than using component form here, a common notation is a numerical format. We recall from past experiences imaginary numbers, where you have the a plus bi format, where a is the real component, b is the imaginary component, using something similar to that. Another notation that we have, just for representing vectors, is this ai plus bj format. I is going to be the unit vector in the horizontal component. J is the unit vector in the vertical component. A is the horizontal size, or horizontal component. And B is our vertical component. This is a notation that's useful in physics. I've used it myself in advanced vector calculus, and it's just a way of representing it as a number rather than as an ordered pair. So all we need to know is that I is our horizontal movement, J is our vertical movement, A is how much we do, B in horizontal, B is how much we move vertically. It's just another way of writing an algebraic vector. So if our vector in algebraic form, say 3, -7, let's just say that A is 3, B is -7. In this notation, our vector could be written as 3i minus 7j. It is just another way of writing your horizontal and vertical components. This comes into play with our unit vectors, in that this is 3 times 1, 0, scalar multiplication, minus 7 times 0, 1. We've got 3 times 1 plus 0, 3 times 0 minus 7. That's a 7. So this AI plus BJ format is just a different way of writing a vector, an algebraic vector. This comes into play quite often in later studies in multivariable calculus. You may have 3 dimensions, AI plus BJ plus CK, if you have a vector in space, where it's in 3 dimensions, where that is horizontal, that is vertical, and that gets you your depth. We're not going to worry about that right now. All we need, that's just another notation that you'll see from time to time. This came up today as a question, the idea of a negative vector, what that means, how we can interpret that both algebraically and geometrically, and using that in an addition statement. If we take the vector 5, -2, 1, 2, 3, 4, 5, -2, we've got vector A. Negative A, we can think about this using scalar multiplication. Negative A would be -5, -2, which gets us -5, +2. Thinking that vector, we go 1, 2, 3, 4, 5, 1, 2. Same exact vector in terms of magnitude, but it's the opposite direction. So if we have a negative vector, it is the same magnitude, just in the opposite direction. Geometrically, how we can interpret that in terms of, say, subtraction. If we have A minus B, this is the same thing as A vector A plus negative vector B. Now here I've used vector A. If we have a plus negative vector B, negative B is going to be, in this case, 2, 1. Take the opposite of both of those. If we have A plus B, we know the tip to tail method. Well, if we have A minus B, A plus B, we would go back 2, down 1. There's plus b, but minus b will add the negation. We'll go 2, 1. So forward 2, up 1. And our resultant is from the original point all the way to the end. A negative just moves in the opposite direction. Now, the last type of problem that we're going to be looking at right now is what we call static equilibrium, or sometimes tension problems. So here I have an example. We have a 1,000-pound weight supported by 2 wires going up, connecting to the ceiling. Now these wires, our task is to figure out the amount of tension that is being supported by each one. Now these 2 wires are attached to the ceiling at a 25-degree angle on one side, a 40-degree angle on the opposite side. Now if the 1,000-pound weight is being supported, it's not being moved at all. It has 0 change in direction. It is not swaying left or right. It is not moving up or down. This is what we call static equilibrium, and the idea behind this is everything is balanced out. Say you have a 3-way tug of war. In this case, we have 3 forces that are acting on this situation. We've got force 1 is from the tension from the weight up towards the left, holding the wire in this sense. Force 2 is from this point, vector up. And force 3 is the weight pulling straight down. Now when we have a static equilibrium problem, we have 3 vectors. Everything is balanced out. So the sum of the 3 vectors is going to be 0. So we have force 1 plus force 2 plus force 3 is going to equal the 0 vector, 0, 0. Everything is balanced. How do we find that? Well, we're going to set up a system of equations. So using this, we're going to identify 3 different vectors, algebraic vectors. Force 1, well, we see that we've got a 25-degree angle here. Well, that makes 25 degrees with the ceiling. By alternate interior angles, if I impose a coordinate system here, this is 25 degrees. And the angle of force 1 relative to 0 degrees, that is going to be 155 degrees. So 180 subtract 25. Alternate interior angles, 25. So force 1 is going to be whatever the magnitude is. I'm going to label it force 1 for right now. Cosine 155 degrees. F1 sine 155 degrees. We have an algebraic representation of force 1, where F1 is the tension on that wire. Vector 2, since this is 40 degrees, down here we're going to have 40 degrees by alternate interior angles. So I can algebraically represent this vector as being F2. I'm going to use that for the magnitude on force 2, or the tension on vector 2. Cosine 40 degrees, F2 sine 40 degrees. Now lastly, F3, we know the magnitude of F3. It is 1,000 pounds straight down. So my magnitude is 1,000. And algebraically, cosine, well, the angle straight down is 270 degrees. So I've got 1,000 cosine 270, 1,000 sine 270. Now here's where the static equilibrium problem comes in. If we add these 3 vectors, everything is balanced. We get 0, 0. Now adding vectors, we add the horizontal components, we add the vertical components. So let's go through that. We have F1 cosine 155 degrees plus F2, a second unknown, cosine 40 degrees plus, now 1,000 cosine 270. Cosine 270 is 0. 1,000 times 0 is 0 equals 0. There's our horizontal components. Vertical components. We've got F1 sine 155 plus F2 sine 40 degrees plus 1,000 sine 270. Well, sine of 270 degrees is -1. 1,000 times -1 is -1,000. So we have minus 1,000. I will add that to the other side. We have equal 1,000. Now this makes sense in that these two wires are supporting vertically that weight. Horizontally, these two are causing zero motion here. So these two wires balance each other out. We have a system of equations. This is just a number, a number, number, number. So working this out, solving this as a system of equations, I'm going to take this first equation, solve it for F2. You could solve for F1. We could use elimination method. I'm going to solve by substitution. F2, if we subtract F1 cosine 155 and divide, we have this is equal to negative F1 cos 155 divided by cosine of 40 degrees. I will use this and substitute into the other equation, solving a system of equations. So we have F1 sine 155 degrees plus F2 is negative F1 cosine 155 over cosine 40 degrees. Now, I'm going to save my calculations till the end, times sine of 40 degrees equals 1,000. What I see here is sine 40 over cosine 40, and I can also factor F1. So we have F1 equals, F1 multiplied by sine 155 minus cosine 155. Sine of 40 over cosine of 40 is tangent of 40 degrees equals 1,000. Dividing, we can find the force on the magnitude of the force on vector 1. We have, bad screenshots, 1,000 divided by sine 155. I am in degree mode. Make certain that I close my parentheses, minus cosine 155, tangent 40. I have the magnitude of force 1, 845.2 pounds of force. Force 2 then, force 2 we've got is negative F1 cosine 150 over cosine 40. So we've got F2 is negative 845.2636 times cosine 155 divided by cosine 40. We get 1,000 pounds of force. So there we have it. We've got a static equilibrium problem. The idea, the main key behind static equilibrium is that we have a sum of multiple vectors equals the zero vector. So we can find the different angles, we can find the magnitudes, save the world. See you tomorrow.